In this video, I'm going to do one significance test for a z-test for means. The Dealey laboratory analyzes specimens of a drug to determine the concentration of an active ingredient. Such chemical analyses are not perfectly precise. Repeated measurements on the same specimen give slightly different results. The results of the repeated measurements follow normal distribution quite closely. The analysis procedure has no bias, so the mean of the population of all measurements is the true concentration of the specimen. The standard deviation of the distribution of the analysis method is known to be 0.0068 grams per liter. The laboratory analyzes each specimen 3 times and reports the mean result. The client sends a specimen for which the concentration of the active ingredient is 0.86%. Dealey's 3 analyses give these concentrations. Is there a significant evidence that the true concentration is not 0.86%? Let's check this out. Our first step is to write our hypotheses. So our null hypothesis is going to get linked back to our previous information, 0.86. That our null, our mean is 0.86%. Now, our alternative hypothesis is that the mean is not 0.86. So that's what we're dealing with. Now we got to figure out what mu represents. Mu is the mean concentration for the specimen. So that is our null hypothesis. We need our null, this is our alternative hypothesis, and we have to describe what mu is. Now, our next part is our conditions. So for our conditions, we have SRS, we have independence, and random and normality. So does the data come from a random sample? Does it say anywhere random sample? Doesn't say. So then you just write data does not come from random sample. So that tells us that we might not be able to generalize this to the whole specimen. All right, so now we want to know, are these independent? So to use our standard deviation, we have to assume that there's more than 30 samples if we're sampling without replacement. So we assume there are more than 30 samples. For independence. And then finally, normality. For normality, we have to address that since these come from a normal distribution, our sampling distribution will be approximately normal. So the sampling distribution is normal because the population is normal. All right, so now we get to the calculations. So in our calculations, we wanted to find that it's not significant. So since it's on both sides, we have to check the bottom and the top. So So that means we're going to have to multiply 2 times the probability that our x bar is either greater than or less than 0.86. And we have to figure out if it's going to be greater than or less than. So first we need to find the mean of those values. So 0.8403 plus 0.8363 plus 0.8447. I got an average of 0.84. So, so here, since our middle is 0.86, 0.84 would have to be here. So we want to find the probability that x is less than or equal to 0.84, and then we multiply that by 2 to get this top end. All right, now to find that probability, I'm going to take 2 times my z-score is less than or equal to 0.84 minus our mean of 0.86 over my standard error, which is 0.0068 over the square root of 3. And that's going to be 2 times the probability of my z-score is less than or equal to. Let's check this out. All right, we got a z-score of negative 5.09, and the probability that's less than that is negative infinity up to negative 5.09. And then if I multiply that by 2, I'll still get a very low number. I got 0.000000358, so on. So that's a very low value. So in my interpretation, we reject our null hypothesis because our p-value of 0.000000358 is below our alpha level of 0.01 in this particular problem. So once we're done, we have to think about what did we find out. We have evidence that that specimen is not 0.86. So we have evidence that the specimen is not 0.86. That's what we wanted to figure out. Hope that made sense.